Okay, thank you. First of all, good evening to all of you, all the participants. Thank you for the nice introduction. Once again, welcome to this FDP session on supercomputing. We are in fact very delighted. Couple of days ago, most of you already attended the specific topic which is related to architectures, where we focused on different architectures, how the combination of GPU, CPU, and other processors, co-processors, and accelerators can form, and different architectures, how they are going to impact the way uh, nature of problems are solved, because we have multiple types of HPC problems, and which class of problems with what kind of architecture. And we also covered a little bit of use cases toward the end. We just highlighted without going into details. And hopefully, over the last 3 days, you have covered much more in that direction. Now, having come to the point where the HPC is in use, and what is the benefit of that and what can be done, the most important aspect is at what cost. This at what cost um, we are looking at in a very different way. The cost can be straight away in terms of monetary expenses, but that is not good enough. We are already talking about various kind of environmental impact of every energy that is consumed, every joule or every kilowatt. We are looking at the thermal pollution, noise that it is creating. We are looking at the greenhouse emissions and so on. So we are looking into a different way. So when we look at the supercomputing list that is published, the top performing, we also have green computing list also being published, and which means we are looking at one side, whatever you are consuming, the energy has to be green. The other side, can we consume lower and lower and lower energy, so that it is more environmental friendly. The earth and as a consequence, humanity can survive longer, and we can carry our society and humanity for a much longer time with a sustainable ecosystem. That is the focus for today's discussion. So I have with me my colleague Dr. Asfija. My apologies for not adding him to the initial list of speakers. He is extremely busy with the National Quantum Computing Mission. He is our mission director across PAN, CDAC, and quantum technologies. But earlier, before quantum became mainstream, he is also an expert in cloud computing and how to distribute various workloads in a cloud, and an expert in all kind of technologies related to scalable computing. So he is joining with me. Thank you, Dr. Asfija, for joining and supporting me in this FDP. And
Thank you.
yeah. So coming back to this, sir, it was going well. The second slide, please.
Yeah.
So as I already highlighted, energy consumption is one of the most important aspects. And if you really look at it, we are on the screen showing currently some of the top 5 kind of supercomputing systems that are currently in operation. And it shows the number of cores, not the CPUs per se, because nowadays each CPU has got multiple cores. And anywhere from, you can see the top 5. And look at the power that it is consuming. Uh, an amazing 30 megawatts, and the lowest being 9 megawatts. So basically, we are looking at a mega power plant just to run a supercomputing thing, which actually comes to the point: are we solving the right problem when we are consuming this kind of energy? So it is first of all this slide itself. We can extrapolate and interpret in such a way that when we want to use HPC, it's not be for the sake of HPC. And we all should move away from a scientist mindset to a engineer mindset. Which what I mean is, as an engineer, we are trying to solve every problem at the lowest cost, minimizing the cost and maximizing the profit. That is the job of engineer, the cost function versus profit function. This is a fundamental requirement for all of us. So the mindset should be that of an engineer when we get into an HPC. So as we come there, we should see if I'm using a 10 cores instead of 2 cores, we should really see do we need a 10 cores for this. So each kind of problem has to be solved in an appropriate system using the lowest number of compute power and cores. So that is one aspect from application development. The second one is our implementation of the algorithm or the solution methodology optimal in terms of energy that is utilized in solving the problem. So energy footprint has to be minimized, which is equivalent to number of computes. As you look at it, can we reduce the number of exponentiation and replace with simple addition, subtraction, or some other methodology? So we know which are the operations that cost the highest amount of energy when we do any program, not necessarily supercomputing. So the algorithm implementation, what operations we use to achieve the target becomes another aspect. And the third aspect is when we are looking at such an workload, we need to have different types of optimization between shared memory versus dedicated memory versus decentralized memory, so that every compute also requires access to the data. So the data mobility across both is another thing to look at it. So as much as possible, the data mobilization should be minimized, so that the not only the seek time, latency time reduces, it also improves the energy efficiency. These are all purely from the point of view of application developers and algorithm providers. But then there are also system software people and OS people, operating system designers, who provide a set of software tools which need to be optimized. So we are looking at today compilers that do 5 passes, sometimes several rounds of passes to optimize. And when you optimize that, for that matter, we are looking at things like, are you optimizing to the OS, to the type of underlying hardware, not just the CPU, but the entire architecture? What kind of memory it is being used? What is the distance between the memory, between the core CPU and the thing? How good the high bandwidth memory is connected to the core and the CPUs? How inter-core communication happens, inter-chip communication happens, inter-socket communication happens, and what is the energy consumption for it? And what is the voltage rails that we are looking at it? So suddenly it is no more just a software programming for HPC, but something you are actually situation aware of the entire ecosystem. So the optimization has to be global from energy consumption perspective. So I just mentioned two of them. There are many more. How the systems are cooled. That is the reason we see some of the data centers today they are saying it is underwater or under the sea. Are naturally in a cool environment, so that the no temperature is taken care, the heat. So if you look at it, these are various things. So what we'll do is we'll try to highlight some of the aspects here. We'll give an appreciation of it, so you become mindful of what you do. Sir, if next slide, please. Uh, Sir, next slide, please. Yeah. So this slide very particularly talks about the data movement, which I just now highlighted. So how the data moves within the ALU, across the data processing pipeline, across the instruction processing pipeline, the cache, the access to the virtual memory, the paging, and then actually the file system itself at the back end, whether it is PFS, whether it is NFS, whether it is GFS, it does not matter. But in the end, we should know what kind of data is being moved, how much of data is being moved. More and more, we are seeing the need to have a in-memory compute so that the mobility of data is minimized to the lowest. This is something extremely important when we look at various programming aspects. Even in the so-called big data analytics, a lot of in-memory compute systems are coming. The algorithms are gaining popularity. There is a reason behind it, which is one side is the timing issue. The more farther away you are from the actual CPU, the distance in terms of seek time and latency time in total. Um, then the other aspect is going to be on the compute power itself, how much it takes. So time, power, all of them play a very major role. So that's the reason we should have minimal data movement. A not openly or directly understood by this is also the security issue. Today, if you look at any cyber security guy, they do side channel analysis. They try to from the side channel or just heat that is generated pattern, what kind of data is moving. So minimizing data actually makes you operate your compute in a stealth mode, to so to say, which actually improves your cyber security posture, which is extremely important but not openly told or discussed benefit when you reduce the data movement. Probably that is one thing, probably we are not keeping an eye on it, or this is not the first priority when we design a solution. But if somebody is looking at something that really makes a difference, these are the aspects that we need to look at it. So the data movement has to be minimized, and in-memory computing is gaining popularity, and that is the takeaway from this slide. Sir, next slide, please. So the next aspect that we are looking at is fault tolerance, because here what we need to do is that um, when you are loading a high performance computing thing, um, in if there is a disruption or any failure, restarting and doing it is going to be uh, both cost and time sensitive, and it is going to be extremely high cost. And the time delay that it takes. For example, if I'm using my supercomputer for a weather prediction, a restarting of the prediction means I lose the window of being predicting the weather on time, and the delay could be catastrophic. Even otherwise, if you are looking at today, we are looking at various digital twins to monitor various processes and various equipment operations optimization. So any restart is not something that is possible. So we have to look at how the entire system is fault tolerant. In fact, the continuity should be ensured, and so there are various techniques that people use. For example, sometimes there could be a checkpointing technique. So if there is a crash, I don't start from somewhere in the middle in the beginning, but I do it from maybe just one or two cycles just behind. So checkpointing could be one option. Then redundancy, active active, passive active, or hot cold, warm kind of standby mechanisms with appropriate watchdog timers, so that the baton is passed on to the active system or alternate system, so the system does not stop functioning. And as a hardware system itself, we already provide in most of the HPCs by design, the redundancy is multiple levels. For example, the Param series of supercomputer that we have in India under the National Supercomputing Mission, depending on the capacity, in most cases, there are two levels of say UPS. There is one which is for critical operations. Then there is one for the entire system. And behind the two UPS, we have got the generators as a standby, and then we have two power supplies from the utility, which means we are looking at three layers of sources: UPS, generators, and the regular power utilities who are serving the power. So there are three levels of supply itself. Then at each place there is a redundancy. Generator sets, for example, the 20 petaflop system that is coming at Bangalore, we have three generators to support. So it is N plus 2 redundancy in generators itself. Then if you look at Bescom, which is our utility provider, they provide supply from two sources in parallel. So it is not two lines. These are two independent sources. That means utility also has a n+1 redundancy, and then we have the UPS to take care of not to avoid a single cycle miss, so that there is no reboot or reset that is possible happening. So the fault tolerance at the system level already exists. Now, how do you make it happening when the program unfortunately crashes for whatever reason, or something happens because of no memory buffer, overflow, or cyber attack and all? How do we continue working? So fault tolerance is something very important, both in terms of time as well as cost of computing. This is going to be very critical for many of the real-time use cases, be it healthcare, be it weather prediction, and things of that nature. And also nowadays, more and more we are using them under AI and other things, using for inference engine. If the inference is not provided on time, the decision support gets delayed. That is another area which is where we need to ensure that the engine doesn't fail, and we get more or less we are trying to say that the design should be such that the outcome is, if not hard real time, it should be at least soft real time, so that there is no discontinuity or disruption, and the service is always available at a defined quality of service that is accepted. This is what we are looking from a fault tolerance perspective. And next slide, sir, please. Um, So the next one is, how do you optimize? I think, though it is written as parallelism in a big time, I will make it very simple for the purpose of the discussion today. When I started my programming in long time ago, we used to do multi-threading as an option. Even today, it is a very, very popular option. When we do multi-threading, it is very interesting. Uh, how many threads should be spawned given a system? So that is a kind of a question that is going to impact the entire performance. So when we look at it, I did some homework and some analytics. This is maybe a couple of decades ago. Um, uh, okay, can others mute the mic, please? We are hearing some noises. Yeah, now it is clear. Um, so when the threading concept came, uh, uh, we did a lot of work. I used to do some programming using Java those days. So Java JVM uses certain kind of memories for depending on 32-bit. In fact, I started when it was still 16-bit and so on. So the number of threads, after a lot of analysis and thing, we figured out. Now it looks very intuitive, but that time, I was very young and raw. Um, so the first choice was like a very enthusiastic kid on the block. We are trying to make as many threads as possible spawn, and then hope it will work. But the reality is, at the back end, we had, for example, the system I had was um, two CPUs with 4 cores in each of them. Essentially, we had 8 cores in the system that I was running my code with. So when the threads were randomly generated, the performance benefit was actually randomly going up and down. Initially, there seemed no correlation between number of threads versus the performance. Um, then over a period, I understood few things. First of all, the JVM has a way of allocating certain memories, X number of MBs and GBs per thread or per inch thing it launches. And then 16-bit has a different kind of a memory consumption allocation versus 32-bit, which has a different kind of allocation. And then very interestingly, if I had 8 cores, um, I tried 8 threads. And interestingly, more than 8 threads, when I did kind of 7 threads, it performed the best. Then at a later point, it turned out when it is n-1 threads with respect to number of cores, the one thread is the like kind of one core is not doing anything else, but it is doing the complete management and it is taking care of the all other background tasks beyond the program that you are running, because there are number of tasks the OS has to perform, which keep happening at the back end. And there are, of course, a lot of things that are monitoring at the back end, and also the system log generation. So many other things are happening. So one core gets completely utilized by that. So the remaining seven basically get a dedicated core for each thread. And if you use the right memory models, we are getting the best performance. So the realization for a specific type of program, writing a code in Java uh, for that kind of two CPU quad core each, n minus one or seven thread became the best performing thing. So you took a bit of iterations and a bit of analysis to understand why the speed up or efficiency is happening depending on how the program runs, how the architecture is, what the OS is, what the compiler or the Java virtual machine or whatever is the backend in the OS is, how the memory is organized in the heap memory and so on. If you are using database, particularly when a large data is used, something those days, in RDBMS, we used to define something called the P of percentage free. So the percentage free, what percentage you keep it free, that also adds to the efficiency. So understanding this gamut of things is very, very important. So when you want to parallelize, when you say threading, basically we are trying to parallelize, do something in parallel. We should figure out what kind of parallelism is needed and how much parallelism to be done. If you overdo it, maybe many of you are aware of the Amadal's law. The Amadal's law talks about the benefit of parallelism versus the cost of managing the parallelism. Because you have to do context switching, you have to actually spawn that many, you have to scheduling related issues, process has to put to, suspend and put to sleep, and then we have to wake up the other process that is being launched from idle to active. So a lot of things that need to be done. These overheads will cost the CPU time and the energy. This is very important. So what kind of parallelism and how much to parallelize is a very, very key aspect. This is the purpose of this particular slide. Next slide, sir, please.
इकोनॉमिकली वीकर सेक्शन वही तो बोला ईडब्ल्यू
Sir, next slide, please. I'll skip this. I think this is more or less covered through a long talk. Yeah. So here now the couple of other points that are coming in, that is related to HPCs as the powers became, power gazellers. The question of, heat management. So nowadays, instead of dissipating the heat is being used for something else, including energy generation itself. This is one part, the thermal aspect, and it has resulted in a large number of new technologies being developed. For example, today we have a liquid-cooled system, and within that also we have liquid flowing through a pipe like a heat sink versus the immersion kind of system where the entire hardware is immersed in a liquid, very specialized liquid, which keeps it cool. And then we are now talking about heat sinks that are using new materials, including nanotubes and nanostructures. The packaging itself is done in such a way that the heat dissipation is more, and the hotspots are reduced and they are more distributed rather than concentrated. So the thermal management as a new field for HPC has evolved. And in fact, if you attend any of the HPC events, conferences and events, one of the major thing you'll find, a number of vendors will be displaying their cooling solutions and thermal management solutions and energy management solutions. And as we do that, the efficiency of the source itself, how much you are using. For example, one of the things that we talk about in HPC is IT load versus non-IT load. So, which clearly indicates that the HPC system is not just about the compute, but the entire infrastructure. So, how much the total load that matters a lot. Sometimes the system may be very efficient, but the cost of the rest of the ecosystem to keep the temperature low of the premise, dust free, and all kind of things, and noise free, that may actually cost you much more than the just heating and cooling problem. So the non-IT part becomes a very important thing. That is where how the energy is used and the thermal design, entire data center design itself has become very interesting. And uh, people are trying many things in this area. HPC is no more a realm of computer science and electronics and electrical people. It is very much now a mechanical, civil, structural, material science, all kind of things. That is no part of it. So it is truly a multidisciplinary thing that we are into as we get into the supercomputing era, where we are now going from petaflops to exaflop, and already program people are thinking about what will happen when we go to jetaflop. Okay, of course there are some path-breaking thinking in terms of energy coming up. That um, I will leave to the next generation, Dr. Asvija, when his turn comes. So for now, we'll go to the next slide in this. Please, sir. So kind of what we need to look at today is where should we focus our research on. One part it is already very clear that our algorithms and design should be aligned to the pipelined architecture or whatever microarchitecture of the supercomputer that you are using, and the way data access is there, whether it is and how the system is designed. Is it a shared distributed memory, or partially dedicated and partially shared? Then how do you synchronize those memories? How many levels of caching, and how much of the RAM is going to be volatile, and how much of it is going to be non-volatile, and so on. So all of them are going to matter a lot, for sure. Um, but in the end, can the processor consume less power for a given compute? So that is the thing that we are looking at on one side. Then the cooling system itself. In fact, interestingly, we are actually having a project where when the queue manager of all the jobs, it basically learns using some AI technique what kind of loads are in pipeline and what kind of predicted loads are there based on the past, and how we can optimize how many CPUs should be even in active mode, so that even if there is a little bit delay, so if you actually do a per or CPM of scheduling critical path method, so we actually will know what is the lag available, slack time available between tasks. So if you know that, maybe a task can wait, and instead of waking up CPU, which will consume power, I can put a node to sleep, because the available slack time, if I accommodate it right, maybe no n minus one nodes can actually do the perform the computing rather than all the n nodes. So that one node permanent, because waking up a sleeping node and putting back to sleep itself is a energy consuming process that has to be cut down. From that perspective, how do you do system that keep themselves cool? So let us say I have 1,000 nodes, and we are able to run all the requirements using 900 nodes. So if we can make sure 100 nodes are always sleeping for a given duration without randomly waking up and going back to sleep, then probably all the systems are working for 90% of the time, 10% they get a sleep time. That way, the lifetime of the entire system is extended, and each system gets a uniform, on time versus off time, which means the aging of the system is uniformly done. so that somebody is not some node is overloaded which fails faster, and another node is not even switched on or not optimally utilized. Those kind of things can be taken. So they are all very much related to the scheduling part of the jobs that has to be looked at. And the algorithm themselves, the energy aware, which for example is in-memory compute, and the type of operation that we need, can we take care of that? Then not but last but not the least is, for example, what kind of thing? Recently, there is a lot of talk on do you need really a full-fledged GPU for AI? Data training and training the AI models, it's a big question mark. Suddenly, someone is saying that we can do a 10% of the GPU power that is currently being claimed by somebody else. So that basically means that if you do it right, probably there is a huge scope for improvement when it comes to doing things right from the point of view of complete energy that is needed for given task. Particularly AI side, now it has become very popular, but we can extend it for each and every domain or every type of application that we are talking about. That is an amazing thing, and we know for sure that from inside we always knew that the GPUs are not fully utilized, and there is only a certain part of it is being utilized for AI models and training. But now this has become a talk of the town, and there are a lot of debates, and really open-ended things are already in place, which is kind of a very good thing to happen. And I'm personally very happy with the way things are moving, and we are able to, and we will be able to. We will be able to actually do a better job with a much lower power consumption for what we are already doing. That is what um, we do. And next slide, sir, please.
Sorry to interrupt you, sir.
Yeah, yes, please.
Participants, please mute yourself.
Yeah. So, thank you, madam. Thank you for seeing, intervening, and quickly. Now, I think we have spent about half an hour or so on a traditional HPC and power and what are the issues. Now we'll change gears and move on to the currently emerging and most popular technology called quantum, where Dr. Aswija is leading, and there, the energy is seen in a totally new perspective and light. So I'll hand over it to Dr. Asfija to take on from here. So he can walk through not only energy and computing, but quantum also in general. So maybe another 40 minutes or so he will go along. Then last few minutes we'll keep it for interaction. But before I request Dr. Asfija, so far, if you have any questions, you are welcome to ask. If there are one or two queries, we can take it now because we'll be kind of changing the core topics. Anybody, any questions specifically?
Participants, if you have any queries, raise your hand.
Yeah, looks like it's not, or people are still thinking through. Maybe I'll now request Dr. Asfija sir. Thanks for joining. Please take over. I'll keep myself mute to avoid any unwanted noise. You can now take over and continue, sir. Thank you so much, Dr. Asfija, please.
Thank you, sir. Thanks for giving that wonderful introduction about the energy landscape in the HPC systems. So, like Dr. Sudarshan mentioned, because of the humongous requirements of the current day HPC systems, in fact, one of the analogies that he gave was on the requirement in terms of megawatts of power that the HPC data centers are currently consuming, which is almost equivalent to the power requirements of a small town as such. So obviously, we need to look at alternate architectures, alternate computing models, which consume much less power and at the same time, which are equally efficient in solving the grand challenge problems that the modern day HPC systems are trying to push the limits for. And that is where quantum computing has shown significant promises, and people have been able to demonstrate the significant power reductions that the quantum systems can offer, and also the kind of computational speed ups these systems can offer. So in that perspective, introducing the quantum systems as part of this lecture, we thought it would be very pertinent to highlight the kind of next generation architectures that the computational systems can offer, both in terms of the energy efficiency as well as in terms of the computational power that these systems can offer. Hello, hope I'm audible.
Yes,
Yes,
sir,
sir.
you're audible.
Okay. Were you able to hear the earlier talk that I was just starting with?
Yes, sir, yes.
Okay. Okay. So during the talk, we'll just give a brief introduction about what quantum computing is all about and how different it is from the classical way or the traditional way of doing computing. And then, of course, we will also look at how to use these quantum systems along with the existing supercomputing systems or the HPC systems as accelerators. Because in the near future, with the kind of advancements that are happening in the quantum technologies as such, we foresee that these systems will be used as accelerators, just like any other special purpose accelerators that we are all aware of, be it the GPUs or the vector cards that work in conjunction with the high performance computing systems of today. We also expect the quantum systems, the quantum computing systems to be working as accelerators, which are optimized for performing specialized tasks along with the existing HPC systems. Okay. What is quantum computing? We will not go into the details of the theory behind how the quantum computers can actually deliver the speed up that we are expecting. Rather, since most of the attendees over here are from computer science and electronics and engineering streams, we will stick on to the kind of computational speed up that we are expecting from the systems, the quantum computing systems, and what is the kind of programming model that these systems employ. This is the whole perspective with which we try to understand using the quantum systems as such. So quantum computers are systems that make use of the quantum mechanical phenomena for performing the calculations. In terms of the basic units of information, the classical systems or the traditional systems, we have something called as the bits, right, which can have the exclusive value of 0 or 1. In terms of the quantum systems, we will have the analogous components called as the qubits, right? So if you see the picture over here in the bottom corner of the slide, there is an analogy of how this entire quantum computing system, how you can draw an analogy with the traditional programming methodology that we are all familiar with. So qubits represent the basic unit of information for a quantum processor as such. So the quantum processor, in fact, operates on this qubits, just like how a CPU will try to do some kind of operations on the bits of information. And we will have to develop or write the quantum algorithms, which will get executed on the quantum processor, which will again get translated to doing some kind of operations on the qubits. Now, what are these algorithms written for? Of course, for solving the problems that we are all very well aware of the same kind of problems that we are trying to solve on our HPC systems or on the supercomputing systems, including some of the grand challenge problems from different scientific domains like drug discovery and the optimization problems in various domains as such, or uh, some of the challenges in the material science as well. What is the fundamental difference between the quantum computing versus classical computing? One of the major differences is that we do the computation, we do the calculation on qubits, which can represent both 0 and 1 at the same time. Now, when I say both 0 and 1 at the same time, this is the kind of parallelism that is already available in the most fundamental unit of information called the qubit, right? Whereas in case of the classical systems, we have the mutually exclusive way of storing the data. The bit can hold either 0 or 1 at any given point of time. Whereas in a qubit, it can have or it can represent the values of 0 and 1 at the same time, which basically contributes to some sort of parallelism which the quantum systems are inherently having. The power for these quantum systems will increase exponentially to the proportion of the number of qubits that are there in a quantum processor as such. Whereas in case of a classical system, the computing power increases in a 1:1 relation with the number of transistors that we have. We have seen how the Moore's law has been obeyed till now, and how it has become extremely challenging to have more and more transistors being packed upon within a single chip. And that is where we are looking at alternate models for pushing the limits of computation. But of course, we do not have practical quantum computers which can deliver utility at scale. So the modern days quantum computers have very high error rates, and they have to be kept ultra cold. Most of the quantum computing systems that we talk today, they all need some kind of refrigerating systems for bringing down the temperatures to somewhat near to the 0 Kelvin as such, right? So in fact, most of the systems today, they operate in the millikelvin range, and that is where the superconducting effects will be very prominently displayed, and it is these effects that are harnessed in building most of the quantum computing systems that are available in the market today. Quantum computers are well suited for some of the problems, at least that is what today's research points at. But of course, this research is quite expanding, and we can definitely expect various other domains wherein the quantum computers also can deliver extremely high performance. But today's quantum computers are well known to give performance for a selected range of applications, including the optimization problems and data analysis, and some cases of machine learning. And this is where, in the near future, the quantum systems are expected to be used as accelerators when compared to them being replacing standalone systems for doing any kind of computational tasks at hand. When it comes to the hardware as such, when I say a qubit which can store the values of 0 and 1 at the same time, how are these systems physically realized when it comes to the quantum hardware? There are multiple, again, contenders when it comes to the way the qubits themselves are created and they are manipulated. Because just like how we have the bits and we try to do some operations on these bits, we will have to create the qubits and we will have to do some kind of operations on these qubits in a quantum computer. So how efficiently we can do this, again, depends on the kind of hardware platform that we choose to implement these systems on. There are multiple contenders. Like I said, the figure on the leftmost side in the slide is what you will usually get, the most popular figure when you try to search on quantum computing in the internet or in the Google search engine. This is the figure that usually pops up. Now, this system is called a superconducting based qubit system, wherein you have a big dilution refrigerator which tries to bring down the temperature to near to the 0 Kelvin range. and that is where the superconducting loops will be used for creating the qubits. And other set of researchers have been working on using photons and the various degrees of freedom that are available with photons, including polarization and then path and many other physical properties of photons that could be used for encoding the information as qubits. And then there are something called as trapped ions and the neutral atoms. Now these are again systems which make use of some of the particles at the atomic scale or in the subatomic scale for encoding the information as qubits. So the point is that there are multiple contenders which could be used for encoding the qubit information as such. Apart from that, what we mean by a quantum computer itself is quite large. The definition itself is quite large, and the model itself is too broad in nature. When we say we are working with a quantum computer, it could be a very specific model of quantum computing that we are trying to refer to. Now, there are different architectures of quantum computing systems that have been displayed in this slide. For example, the black boxes that you see on the top of the slide, it's from a company called as D-Wave. They manufacture the systems called as quantum annealers, which are very well suited for solving the optimization problems. And right at the bottom of that system, we have this, again, the famous picture from Google, which represents the superconducting based system. And this follows a particular model of quantum computing called as a gate-based architecture. So when I say gate-based, you can think of the quantum computing systems to have the same kind of logical gates that are used for building the circuits in our classical systems as well. The logical gates like the AND gate, the OR gate, the NOT gate, very similar to that, we will have the equivalent quantum gates in the quantum computer, which follows the gate-based architecture. And this is one of the most widely explored architecture platform for building the quantum systems. Big giants, including the IBM, Google, Rigetti, Microsoft, most of these companies have all been trying to build these kind of gate-based quantum computers as such. Now, other than that, there are other ways of building the quantum computers, including the measurement-based quantum computers, and of late, the topological quantum computers, of which Microsoft has recently demonstrated a successful quantum chip. You might have recently heard that Microsoft has released a new quantum chip. Now, this is completely different architecturally from what Google had released a couple of months back. So the Microsoft chip is based on a model called as topological quantum computation. We'll not go into the details of how this differs from the gate-based model. And then there is again another class of quantum computers which are called as quantum simulators. Now these kind of systems are not general purpose in nature, which means to say that they do not perform all kinds of computational logic as such. They are not suitable for all kinds of computational logic. Rather, they try to mimic the behavior of a specific quantum mechanical system. Right now, where are these kind of systems used? These kind of systems are very heavily used in modeling the quantum chemistry reactions as such, and specifically in the industries like pharma, where these kind of reactions that have to be modeled at the quantum mechanics scale becomes very prominent. The quantum simulators will be very heavily deployed. Of course, the same quantum simulation task can also be performed on the other kind of architecture models that I just described, including the gate-based model and the measurement-based systems as well. Like we have been discussing, the current day trend is to have a combination of both of these systems, the best of what each of these architectures have to offer. If we can combine them to build a hybrid system called as the quantum classical hybrid computing. This is the current day trend. Most of the supercomputing data centers that are operating in the exaflop range today, they're also looking at having the quantum computers co-located as part of the data centers and trying to offer this hybrid quantum classical computing as a service to the researchers in their own countries. So like I said, hybrid computing combines the strengths of both quantum and the classical systems. And of course, quantum computers are designed to perform specific tasks. They are very good at performing those tasks. It doesn't mean that the quantum computers cannot handle universal computational logic as such. They can be designed to handle any kind of computational logic, but they may not be efficient for some sorts of applications as such. That is what it means. Which means to say that the quantum computers could be beneficial for a certain class of applications, but whereas the classical systems or the digital transistor-based systems that we are all currently using, they could still be outperforming for the other classes of problems. And that is where a combination of using both the classical and the quantum systems together makes more sense. Most of the big software giants as well, including IBM, Google, and NVIDIA, they have all been already demonstrating these kind of hybrid systems by integrating quantum processors into the supercomputing workflows. Just like how you develop a standard accelerated supercomputing workflow, which will involve some sections of code which has to get executed on the GPU as such. You use some kind of programming primitive to say that this section of code has to go into the GPU, basically the GPU kernel, which has to get executed on the GPU, and the results have to be again brought back by the runtime to the CPU as such. Now, very similar to that, there are software systems which have been developed which can partition this load in some cases intelligently and in some cases with the intervention of the programmer by using some kinds of programming primitives. And this particular quantum workload can be offloaded to the QPU as such. And once the execution happens on the QPU, or it gets finished on the QPU, the results can be brought back to the CPU or the HPC from which the entire workflow was initiated as such. Of course, it is not as simple as I just explained, because there are a lot of challenges that are involved. Like I just mentioned earlier, the quantum computers work on the qubits as such, which means to say that the way the data is represented is completely different from the classical system to a quantum system. So when I say that workflow involves some portion of compute logic to be offloaded onto the quantum systems as such, what happens to the data? Now the data is typically classical in nature, right? But the quantum systems need the quantum data, right? So this kind of encoding from classical to quantum has to happen. And then again, once the quantum computers have finished their execution, the data, which is again in the quantum form, has to be brought, or it has to be encoded into the classical systems as such. So this kind of data encoding and decoding is a prominent thing that the hybrid systems have to take care of. In terms of algorithms, there have been significant breakthroughs, including something called as the variational quantum eigensolver and a well-known optimization algorithm called as the quantum approximate optimization algorithm. Now, these algorithms, they are inherently hybrid in nature, which means to say that the algorithm has some classical part and it also has some quantum part inherently. So the programmer as such need not spend his effort on what is the quantum part, what the quantum part can contribute to and what the classical system can contribute to. So the algorithm has this inherent hybrid nature, and these algorithms have shown to outperform, the hybrid algorithms have shown to outperform the classical counterparts as such. And cloud-based quantum computing has also picked up the pace. You are already aware that all the major providers, including IBM, Microsoft, and Amazon, they are offering the quantum systems on the cloud, and the hybrid systems are also available on the cloud for the researchers to carry out their research in quantum computing as such. Yeah, what are the application areas? If we look at for these kind of hybrid systems, there are multiple application areas. For example, as I told, quantum computers are very well suited for solving the optimization problems. And optimization as such, you know, has a broad gamut of applications, be it in any kind of scientific or business domain. You have the optimization problems that have to be solved. And quantum computers are very good at solving these kind of optimization problems at scale. And in addition to that, the quantum systems can also offer very good, very significant benefits for cryptography and material science, and of course in machine learning. So I have separate slides on all of these topics individually. So I'll move on to the next slide. Quantum systems have been increasingly, they have been explored to use as an accelerator for the machine learning tasks. Because the way in which the quantum systems operate on the data, like I said, once you have a combination of qubits created, the amount of data that is available for you will just grow exponentially large, right? So which means to say that if you have a large set of data which has to be encoded, then it can be very efficiently encoded in terms of very few qubits using a quantum computer. And that is where the machine learning tasks are expected to offer very huge benefits by using the quantum computers, right? So the quantum data will be encoded using the qubits, and in most of the cases for the machine learning, including most of the popular approaches for machine learning, including the support vector machines and the neural network models as such, the quantum counterparts as such, just by encoding this data into the quantum states, we are actually moving to a higher dimension space. And if you know the internals of how the support vectors machines work, you know that just by creating a higher dimension feature map, just by having a feature map which maps your lower dimension data to higher dimension data, you could do the classification in a very efficient manner by using the kernel functions which can work along with the support vector machines, which again try to do the same kind of operation in the classical systems. You try to map the lower dimension data points to the higher dimension data so that the classification becomes very easy just by having a hyperplane which can segregate the data as such. In this perspective, the quantum computers can offer significant benefits. Like I said, just by encoding the data as quantum states, we are actually moving to the higher dimension data as such, and that offers a significant benefit for the classification problems. And like I have been telling, the optimization problems are very good candidates to be solved on the quantum computers. The linear programming problems or the quadratic programming problems or the scheduling problems, all of these things can definitely get benefited by making use of the quantum computers as such. So what is shown in this slide is a typical workflow of how a quantum optimization happens using this famous approach called as the quantum approximate optimization algorithm. I'll not go into the details of this workflow. Nevertheless, this is not the only way in which the optimization can be handled. There are specific hardware resources that are being built only to solve the optimization problems using the quantum mechanical principles as such. Now, these systems are called as quantum annealers, and they are very good and they are very efficient at solving the quantum optimization problems as such, right? So basically, they make use of the minimum energy principle that we are all very well aware of in the physical systems. So any given system at equilibrium, we know that it tends to move to its lowest energy as such, right? So this particular principle is being harnessed in devising the optimization problems, because most of the optimization problems, if you look at the mathematical formulation of these kind of optimization would be like, you will have some kind of cost function and you will have to find the minimum of this particular cost function with a given set of constraints, right? So you will have some kind of constrained objective function that has to be minimized, either minimized or maximized, right? So using this lowest energy principle, how do you map your problem, the optimization problem that is at hand? How do you map this particular problem to the problem that the quantum systems are very well efficient in solving? So you try to map the variables that are available in your objective function into the different qubits in the quantum computer, and then you just allow the nature to work. And because of the minimum energy principles, all of these qubits or the quantum states would reach an equilibrium state wherein we would have reached the global minima of the entire quantum state as such. And that particular state will of course represent the desired result of the optimization problem as such. So this is the fundamental principle of using optimization in quantum computers as such. And then of course, quantum simulators I have already talked about. They have very broad impact. The basic idea is like, how do we mimic the quantum processes that are happening in the biological systems or in the natural systems in an artificial system as such? And why do we have to do that? Today, many of the chemical reactions that we will have to study, if we try to have the understanding at the quantum mechanics level, then we can definitely come up with a very highly energy efficient way of doing the same kind of reactions as such. And this will also lead to the development of new materials. So the material science also will definitely get benefited from these kind of systems, right? So in order to do these kind of simulations of the chemical processes or the reactions that happen at the molecular level or at the atomic level, we need a controlled system wherein we can try to mimic this chemical phenomena at the atomic scale or at the subatomic scale, which means to say that we want to deal at the quantum scale as such. And that is where specialized systems called as the quantum simulators are being developed. And these systems are completely programmable in nature, which means to say that every state of this particular system can be individually controlled, right? And that is where a chemical reaction that happens in a lab can be simulated exactly at the quantum mechanics level using the quantum simulators. And this can provide a huge level of insights in devising the new compounds as such, or it could be, for example, leading to a breakthrough in developing new technologies for battery designs and the drug discovery, wherein new bondings have to be discovered between the molecules and the protein ligands as such. So all of these complex chemical reactions can be simulated and they can be better understood in the quantum mechanics level by using the quantum simulators as such. Quantum computers, of course, many of you might have heard that once the powerful quantum computers have been realized, they can break the modern day cryptographic systems. That is very true. On the other hand, if we employ the quantum systems as such for doing all our communication, it can also offer a high degree of security in terms of the data that is being transmitted over the communication network. While on one hand, the quantum systems can break the existing cryptographic systems, at the same time, employing the quantum systems by themselves will also lead to a very high degree of secure systems, right? So in that sense, quantum accelerators can have a very game-changing impact in terms of cryptography. Like I said, quantum systems are known to break the existing cryptographic systems. And that is where people have been looking at coming up with alternate models of how we do encryption and decryption. This class of this branch of study, wherein people are trying to come up with their own algorithms or their own ways of doing encryption and decryption, which are resistant to the futuristic quantum computers. This branch of study is called as the post-quantum cryptography. So the quantum computers or the quantum accelerators by themselves can definitely contribute to the advancement of the post-quantum cryptographic systems as such. They can definitely be used for simulating the attacks, the quantum attacks on any of these algorithms that are being newly developed, and to what extent the new algorithms are resistant to the quantum attacks. They could very well be checked, and they could be modified to be quantum resistant as such. And of course, like I said, the quantum systems as such can also offer unconditional security. So you might be aware of the quantum key distribution, or the QKD, which is quite popular for giving a foolproof solution or a very secure solution for solving the key exchange problem in the classical symmetric key cryptographic systems, right? In a symmetric key cryptography system, we know that we have the same key which is being used for both encryption and decryption, right? Since it is the same key that has to be used for both encryption as well as decryption, how do you share this key, the common key between the sender and the receiver, in a secure manner? Because if the key is compromised, then the entire data gets compromised because the same key is being used, right? And that is where the QKD comes to the rescue, right? QKD, or the quantum key distribution, helps to distribute this symmetric key in a very secure manner between the sender and the receiver. Okay, so once this key exchange happens with QKD, the normal encryption and decryption can still continue with any of the symmetric classical symmetric encryption or symmetric cryptographic approaches that we are familiar with, right? Be it AES or DES, any of the approaches can still be followed using any of the classical algorithms that we are all aware of. But the important aspect of doing the key exchange in a secure manner can definitely be made secure by using the quantum systems as such. And then quantum systems can also help in doing cryptanalysis jobs. One of the famous algorithms that everybody speaks of when talking about the quantum computers is called the Shor's algorithm, and then the Grover's algorithm. The Grover's algorithm has an implication on the searching problem as such. And because the cryptanalysis, many of the brute force tactics that are used in the cryptanalysis, they rely upon doing the search on a huge search space as such. Just carrying out a brute force approach might not be feasible at all, right? For example, if you take the example of doing a key search on the AES algorithm as such, if it is using a 256-bit key as such, then we have the search space which is equivalent to 2 to the power of 256, which is a very huge space. And just by having a brute force search strategy will definitely not help at all, right? So in that case, if we employ the quantum algorithms as such, for example, the Grover's algorithm, if it is employed, then it would reduce the search space drastically. Okay, it would reduce the search space in such a way that the cryptanalysis can still be attempted on the existing classical systems as such, right? So that is a kind of advantage that the quantum systems will bring in, and that is where quantum systems are also looked as a threat for the existing cryptographic systems as such. Having seen the different application areas of the quantum systems, both in terms of the energy efficiency as well as in terms of the computational speed up that it can offer. So what are the challenges that are there? Like I said, most of the quantum systems are all prone to noise because the different hardware platforms that I was just displaying, you could see that for creating the qubits and doing some kind of operations on these qubits, you will have to deal at the atomic level or at the subatomic level, right? And this is where the challenges creep in. Now, how do you efficiently create a single photon, right? If you want to encode a qubit on a single photon as such, right? You need a single photon to be created. And then once a single photon has been created, if you want to do some operations on this, if you want to apply a gate, then it means that you're trying to do some kind of operation on this particular quantum state, right? Now, how do you make a precise operation? How do you perform a precise operation on a single photon? Right? So it is this kind of precision that imposes significant challenges, significant engineering challenges in building the quantum computers that can operate at scale. And because of this, there is a lot of noise that gets introduced into the system, right? Because we are still making use of the natural particles, be it at the atomic scale or the molecular scale, or sometimes even in the subatomic scale, right? But nevertheless, all of these quantum particles are affected by nature as such, and nature induces various kinds of noises. So if I try to create a qubit in a particular state, because of the influence from the environment, it would evolve naturally to something else, right? Before I try to do some useful operation on it, or before I try to read out the data from it, it would have got evolved into some other different state. Now, this is called as decoherence. This is happening because of the noise that the environment induces. So this is a very big challenge in designing complex quantum computers. Right? How efficiently you can build systems which are which can handle these kind of noises. And of course, once there is noise in the system, they would of course result in the errors in the programming level, right? So you will have to handle the errors both at the hardware level as well as in the algorithmic level. So you will have to come up with novel strategies for error handling and error correction, right? Like I was just mentioning. So the qubit would evolve to a different state. So if I try to do a readout on that particular quantum state, then it will be giving me a wrong result, right? So if the original qubit was created in a state 0, it would have evolved to some other state. And if I try to read the information from that, it might give it as 1, right? So this is called the bit flip error, right? So the original intended qubit was supposed to give a value of 0, whereas because of the error or the noise, it has evolved and we are getting a value of 1, right? So like this, there are multiple errors that the environment can induce. And there are other errors which our system also will try to induce. The kind of operations that we try to perform on this system, they also introduce some errors. And since we are dealing at the subatomic level in most of the cases, the instruments that we make use of also introduce many kinds of errors. So this is where handling errors and the noises becomes a very significant challenge. System engineers have to pay attention. So all these things that I was just describing of the challenges of creating a qubit in the physical system and then try to manipulate on them. These are all called as the physical qubits. These are the qubits that are available in some kind of physical system. So you make use of a physical particle as such to encode this particular information. But these physical systems are prone to noises, and that is where people have been thinking of using logical qubits. For example, can you combine some amount of these physical qubits and can you build a error-free logical qubit, right? So a logical qubit will comprise of many physical qubits, of course, by running some kind of error correction code on them. So creating logical qubits, of course, requires many such physical qubits to be made available in the backend, right? So if you want one logical qubit, it might happen that we might require some 12 physical qubits or 25 physical qubits to be available in the backend. So to scale up the requirement on the number of qubits, again, is a bigger challenge in terms of engineering. So the scalability and of course the quantum control, right? We will have to build the systems which can operate in a very precise way. We will have to build the systems that can operate on every quantum state as such. You should be able to address a particular quantum state at that particular subatomic particle has to be manipulated. So the quantum control systems have to be very efficient and they have to be very precise. And then, like we all already saw, the fundamental way in which the data is represented is something completely different from the classical systems. And the way in which the computation happens is also completely different. Today, all the quantum computers today, they factor in the fact that there is no quantum memory available, right? Because building a quantum memory again is a very big challenge by itself. So most of the quantum computers today, in fact, all the quantum computing paradigms that are available today, they are all non-von Neumann. They follow the non-von Neumann architecture as such, which means to say that the programming model inherently assumes that there is no quantum memory as such, right? Now, because of all of these limitations, you will have to completely rethink how you write the quantum algorithms as such. So it is not a one-to-one mapping of you take some classical algorithm and you just come up with the quantum equivalent of that particular algorithm. Right? You will have to completely reason and think how to exploit the quantum mechanical properties for introducing the parallelism or getting the benefits of the quantum computing systems as such. And the other challenge, of course, which I already highlighted, how to bridge the classical to quantum divide. For example, if you want to make use of the systems as accelerators, then how do you efficiently come up with the interconnects which can intelligently encode and decode the quantum data, right? And then significant enhancements also are expected from the material science level, because like I said, we are using the particles at the subatomic level to encode the information. Now, if there are revolutionary breakthroughs that are happening in the material science, which can give us some kind of systems that can operate at room temperature instead of relying upon the systems, the existing systems, which can display the quantum behavior only in the superconducting regime or at the very low temperature regime as such. So in that sense, we need to have radical breakthroughs that can happen in the material science, which will give us some kind of new age materials which can deliver the quantum effects to us in a controlled manner in the room temperature. So that will definitely lead to a significant advancement in the proliferation of the quantum systems. The future outlook, of course, in the very near term, there is already a widespread adoption. Like I said, many of the data centers worldwide, they all have quantum systems to be deployed in conjunction with the HPC systems. And many of the industries also, they have already started using the quantum systems for many of the optimization related problems. So that is where there has been a lot of effort currently in developing the error correction strategies. In the near midterm, we will have the hybrid processes, which will work by making use of both the classical and the quantum workloads, right? And in the long term, we will have the full-fledged quantum processes, and there will be a much wider industry adoption. And of course, in the far term, this would lead to ubiquitous quantum computing, which can also have the promise of replacing the existing computing systems with completely quantum systems as such, which can of course lead to new scientific discoveries and contributing to the economic growth as such. So that was the brief introduction about the quantum computing systems as such and their applications. I would just conclude my talk by taking a few minutes of time in introducing the quantum technology products that CDAC is currently working on. CDAC has been working in multiple areas of quantum technologies, including quantum computing and quantum communication. Quantum computing, like I told, we have been involved in developing both at the hardware as well as in the software layers. In the hardware, we have been specifically focusing on developing the superconducting based systems as well as the photonic based quantum computing systems. And we also specialize in developing the control hardware, which I was highlighting in my earlier talk also, on how important and how crucial the quantum control systems have to be, right? So CDAC is developing the control hardware for both of these kind of architectures as such. And CDAC is very well known for building and offering the HPC systems as such. And it leveraging this expertise, we are also looking at how the quantum systems can work as accelerators and what are the technologies that are required for building this gap between the classical and the quantum systems as such. We also understand that the quantum systems are not available and they're not affordable for everyone to access as such. And this is where having a software simulator, what we call as a quantum circuit simulators, which will try to mimic the behavior of a quantum system by completely running on a classical system, right? So this is a software program which runs on a classical system, which is called a circuit simulator. Now these circuit simulators are of great use for someone who wants to just get a feel of how to do quantum programming or how to develop new quantum algorithms, right? So in all these scenarios, we have a line of products, including the product called as the QSIM, and then there is something called as Quniverse. So all of these products are specifically aimed at this novice audience who want to start programming by making use of the quantum circuit simulators as such. And we are also in the process of setting physical superconducting based quantum system in the range of 50 to 100 qubits at our Bangalore campus here. And in quantum communication also, we have been working in multiple projects. Very similar to the quantum circuit simulator, we also have a quantum network simulator, which tries to mimic the functionalities of various quantum communication protocols, including the QKD as such. In addition to the simulator, we are also involved in setting up the physical quantum key distribution network as part of an initiative called as the Makan. And this initiative happens to be one of the very few such initiatives worldwide. And we have been able to successfully demonstrate the QKD in the metro area regime as such by connecting multiple institutes in Chennai. And we also have plans for extending this network to a long distance quantum communication network, which will lead to the further advancements in what we call as quantum internet by extending the ranges of this communication network to thousands of kilometers. And CDAC is also working on building aerial QKD systems or free space QKD systems involving moving targets as well, including the drone-based systems as such. We also have a full-fledged software stack which caters to the requirements of both computing as well as communication. It can work with simulators which can work on the classical systems. At the same time, the same software stack will also be able to submit the jobs onto a physical system and get back the results onto the user desktop as such. And this entire system is available as a cloud solution, and anyone who just has an access to the internet will have the power of the entire quantum computing system at his desktop. Like I said, post-quantum cryptography is another area which is very important, and CDAC is working in this area also in developing novel algorithms which are quantum resistant in nature. So we are working on developing our own quantum safe algorithms, our own PQC algorithms, and we are also looking at how these algorithms can be efficiently implemented in accelerated hardware like FPGAs and other hardware instruments, and also how these PQC algorithms can be burnt into an USB dongle, which could be used for creating a public key infrastructure as such. The existing USB based dongles that you are all familiar with for signing, if they can be replaced with quantum safe algorithms as such. So that has been our focus, and we are working in this area as well. And in addition to that, we are also working on developing a completely quantum safe TLS protocol to make the quantum internet communication quantum safe as such. So these are some of the products or the projects that CDAC has been actively working on in the quantum technology areas. So with this, I'll conclude my talk. And if there are any queries at this stage, I'll be happy to answer.
Sir, there is a in chat box there is a requisition. Please offer training and collaborative research for faculty members and PG students.
Definitely, ma'am. CDAC has already been conducting multiple faculty development programs, specifically in the area of quantum computing and communication. We will definitely be more than willing to extend this program to all the participants over here also.
Sir, good evening, sir. This is Murali Bhaskaran.
Good evening, sir. Good evening.
Very nice information, sir. I am very proud of CDAC. And India is doing very good research on quantum.
Thank you,
So
sir.
actually, we as engineering college faculty will still visualizing how the quantum computer would be. So
Yeah.
if you have the opportunities every 3 months or every 6 months once, the faculty
Yes, sir.
can visit and see the development of the quantum computing. Thereby, we also will collaborate. You have mentioned the 7 research areas, so
Yeah.
we will also take part in the research and then do some things. You are in which office, sir? Chennai or somewhere else, sir?
I am based out of Bangalore, sir. CDAC Bangalore. And
CDAC
like I
Bangalore.
said,
Okay.
yeah, like I said, in let us say some 6 months of uh, time, we will have a physical quantum computer in the order of 50 to 100 units deployed here in Bangalore. And once the
Oh.
system is fully operational, you are most welcome to visit the facility and
Yeah,
get a
March
feedback.
1st, there will be a IAC Bangalore visit. Open day is there. Is it in within IAC Bangalore or separately? CDAC is separate, sir?
I am not aware of that particular program which you are referring to, sir. But we are working closely with IASC on the various other quantum initiatives. We
Okay.
will look at the specific event that you are mentioning.
So in your website, you will you give information about this, no?
Yes, sir.
Uh,
Yeah,
in
yeah.
the, because I actually applied the CDAC collaborative program in Pune.
Ah,
But
okay.
I am unable to attend due to my personal things. I applied and
Oh,
I was not selected, but I
oh, oh.
didn't go that. I am
Okay.
interested in quantum computing, so that's why I am asking, sir.
Definitely, sir. Definitely. Definitely. We encourage you to.
One basic doubt, sir. Shall I ask?
Yes, sir. Sure.
Yeah. See, actually, one qubit will store 3 values, sir, or 2 values.
Sir, I mean, it is very difficult to straightforwardly answer that. But in terms
Okay.
of programming as such, if we are looking at how we store 0 and 1 in terms of a bit, you
Yeah.
can imagine that you will have both 0 and 1 stored at the same time. That is what we are telling, sir.
That's still I am unable to, because
It is
when you toss the
counterintuitive.
coin,
Yeah,
when it is
yeah,
in the hand, we know the what is the position. When it is
correct,
the
correct.
top, we know the positions. But in
Ex-
between, it will rotate
yes,
whether it is
yes,
head or tail. So
correct.
in that position, if you read the value, we will
Ah,
get any one of that, either head or tail.
exactly, sir.
But we
Exactly,
cannot
exactly.
get both.
Yes. Now,
It is
the
time
concept is,
dependent. It is
yes, sir,
time dependent.
correct. The
So
concept is
at
very similar
particular
over
time
here
we'll get
also.
head, or another particular time we'll get tail. So still
Correct.
I'm not convinced that how both values you can read at a time. That is my worries.
Yeah. No, you are right, sir. You have given a very perfect analogy also. Uh,
Yeah.
Now, when the coin has landed on your hand, of
Okay.
course, like you said, it will be either zero, I mean, either heads or tails, right?
Yes.
So that is what we say as the qubit will collapse to either 0 or 1 when we do something called as a measurement. Now, I did not go into those aspects because of
Okay, sir.
lack
Okay.
of
Okay.
time
Still,
today.
because that the
But
basic
the
things.
idea is this, sir. I'll just explain the broad idea.
Yeah.
Now, like you told, when the coin has been tossed and it is still in the air,
Mm.
it is in a superposition of both of these heads and tails, right?
Correct. Correct.
And it is at this stage we try to do some kind of operations. Okay, so
Okay.
when you try to do the operations before it has landed on your hand, it will still be holding that superposition in the state, right? So the parallelism is still available in that particular instance. Once it has landed onto your hand, the superposition would have got collapsed, and that is where when we say we have done the measurement and we will be able to get only one of the results. Whereas when it is still in the air, it is still in the state of superposition, and it is this state we will tackle for doing the operations in quantum computers.
Oh, in quantum computer, still in the air also the value we can read and then do process.
In the air, in the sense I just gave an analogy because
Okay.
since
No,
you
just I'm telling when the spin
just
is
to
rotating.
understand that, yes,
Yeah,
yes,
yeah, correct,
when the
correct.
state has not collapsed either to 0 or 1, in that state we try to do the operations.
Okay, sir. Thank you,
Okay.
sir. Thank you.
Okay. Thank you. Thanks for patiently listening to my lecture. Thank you.
Moving forward, energy is not going to be just the key important aspect, but collaboration and getting into new areas like quantum, that is what going to take us forward. And it is going to be a completely different and new paradigm, which we hope will not only make the earth sustainable, but solve problems in a different way. The question of superimposition came in picture. In fact, those who know digital circuit, there is something called synchronous and asynchronous clock. If you look at it, think of it as all the states available to all in a shared way. So everyone is situation aware. So the propagation delay gets minimized, and you do your compute and use what is appropriate as far as your final thing is concerned. I think if we keep our mind open a bit, go back to our basics, uh, then very soon I think we'll be doing all that, and we should be fine.